Good afternoon, everybody, and welcome to this new online lecture organized in the framework of the Strong 2020 project. Today, we have two guests with us. We are pleased to welcome Professor Charles Horowitz, theoretical nuclear astrophysicist. He is working at the Indiana University, and Professor Paul Sauder, Syracuse University, who is working on nuclear and particle physics. They will describe the PREX laboratory experiment that clearly measures where neutrons are located in an atomic nucleus. This has implications for neutron stars. Despite being a million billion times larger than a nucleus and having half again the mass of the sun, neutron stars are made of the same neutrons with the same strong interactions. They will compare PREX results to gravitational wave observations of the merger of the two neutron stars with the LIGO and Virgo detectors. So a few words about the Strong 2020. This is a European project dedicated to the strong interaction at the frontier of knowledge and has received the funding from the European Union's Horizon 2020 Research and Innovation Program. It is a rather big project that involves 44 institutions from 14 European member states, one international EU interest organization, CERN, and one EU candidate country. Together with host institutions of 21 other countries without benefits of EU funds, the project involves around 3,000 researchers from 36 countries. So you can write your questions for Professor Horowitz and Professor Sauder in the chat, and at the end, we will answer to some of them. Now I leave the floor to Professor Horowitz.
Great, so thank you very much for the chance to talk. I want to talk about studying neutron star matter in the laboratory. Neutron stars are born in supernova explosions. So it's an explosion of a massive star. If you start here, this is an artist's conception of the view low in the east, early in the morning of July 5th, 1054. The dim thing over here, that's the moon. And the very bright star that was visible in daylight that didn't used to be there, that's the Crab supernova. So that's a single exploding star. If you look in this region of the sky today, 1,000 years later, you see the Crab nebulae. So that's the outer 90% of the star that was hurled out into space at about 1/300th the speed of light. And so over the course of the 1,000 years, the Crab nebulae is about 3 light years across now. And if you look in the center of the Crab nebulae at one particular star, and you put a radio telescope on that star, pulsar. So it's a neutron star, mass of the sun, the size of a city, and it's rotating 30 times a second. So that's how the neutron star got born. Neutron stars are made of neutron-rich matter. And so that's what we want to study today. If you compress almost anything enough, the electrons react with protons to make neutron-rich matter. This material is at the heart of many fundamental questions in nuclear physics and astrophysics. What are the high-density phases of quantum chromodynamics? So quantum chromodynamics is our theory for quarks and gluons. Where did the chemical elements come from? What is the structure of many compact and energetic objects in the heavens? what determines their electromagnetic, neutrino, and gravitational wave radiations. We're interested in neutron-rich matter over a tremendous range of density and temperature. Just to get oriented on the density, a white dwarf star may have a central density of 10 to the 7 grams per cubic centimeter, so much higher than the sun, but not nearly as dense as an atomic nucleus. So inside a nucleus, the density is about 10 to the 14 grams per cubic centimeter. And then inside a neutron star, the density is a few times higher than that. So an atomic nucleus has a similar, slightly lower density to a neutron star. And this may be the end for matter as we know it. If you compress a neutron star a little more, it'll collapse to a black hole where the density is essentially infinite. A heavy nucleus, such as lead-208, is expected to have a neutron-rich skin. And if we can study very cleanly this neutron-rich region in the surface of the nucleus, we can study this neutron star matter, this neutron-rich matter, in the laboratory. So here's a model for the atomic nucleus lead-208. So we're plotting the density versus radius. So radius in Fermis. A Fermi is 10 to the minus 15 meters. The red curve is the proton density. So a lead-208 nucleus has 82 protons. So the area under the red curve is 82. And we know where the protons are from scattering electrons, and Paul Soter is going to talk a little bit more about that. The new information is where the neutrons are. So lead-208 has 126 neutrons, so actually 44 more neutrons than protons. And some of those extra neutrons are expected to pile up in the surface region. So out in the surface of the nucleus, there's this neutron-rich matter. And this is matter like inside a neutron star. And so the P-REX experiment measures precisely how much these neutrons stick out compared to the protons. So it's measuring the radius of the neutron distribution compared to that of the protons. Great, so these two diagrams are not to scale. A lead-208 nucleus is about 10 Fermis across. A neutron star, again, it's got the mass of the sun, but it's got a radius, and we'll get to that, is about 12 or 13 kilometers. So this neutron star is 18 orders of magnitude larger than a lead nucleus, but it's made of the same neutron-rich matter. The pressure of the neutron-rich matter pushes the neutrons out against surface tension, and so leads to a larger neutron radius in the lead nucleus. And so that's what the P-REX experiment is going to be measuring. So by measuring the neutron radius, we can learn about the pressure of neutron-rich matter. And this same pressure is holding up the matter in a neutron star against the tremendous gravity. So a large radius in lead is a large pressure, and that large pressure leads to a large radius for a neutron star. So a measurement of the neutron radius in the laboratory has important implications for the structure of neutron stars. So the fact, despite being 18 orders of magnitude larger, a neutron star is made of the same neutrons with the same strong interactions and the same pressure as in a lead nucleus. So what I'd like to do now is say a little bit how we can infer the radius of a neutron star from observations of gravitational waves from two neutron stars colliding. And then we'll compare that to the P-Rex measurement of the neutron radius in that. So a couple words about gravitational waves. In 2015, two large detectors in Hanford, Washington, and Livingston, Louisiana, these two LIGO detectors, detected faint ripples in space and time from the distant collision of two black holes. These ripples are known as gravitational waves and were predicted by Albert Einstein 100 years ago. Think of the distance between my hands. Of course, if I move my hands, the distance changes. But if I keep my hands really, really still, but the space between my hands shrinks or stretches because of a gravitational wave, because of this ripple in space, then the change in the space between my hands changes the distance between my hands, even if my hands don't move. So the challenge is to keep one's hands very, very still and measure the distance between them very precisely. This is the LIGO detector in Hanford, Washington. It's a laser interferometer. There are two 4-kilometer arms, and they don't actually measure the distance between my hands. They measure the distance between two very, very, very high quality mirrors. And what they actually do is measure the length of one of the arms compared to the length of the other arm. And when a gravitational wave comes, it shrinks one arm and stretches the other arm by an incredibly tiny amount. But this is a very, very sensitive detector, and it can detect this extraordinarily tiny change. From these gravitational waves, we can learn about neutron stars and the matter in the neutron star. And what LIGO actually constrained was the so-called deformability of a neutron star. So two neutron stars in a close binary orbit, they radiate these gravitational waves, and that takes energy from the system. And as a result, the neutron stars spiral together. They move closer and orbit faster and faster. And when they get very close together, gravity from one star deforms the other star. And LIGO actually measures or constrains how much a star is being deformed by the gravity of its companion. And this deformability provides a measure of the radius of a neutron star. It actually scales like the radius to the 5th power. So if a neutron star is bigger, it leads to a much larger deformability. So in 2017, the LIGO and Virgo, which is a similar detector in Italy, observed the merger of two neutron stars. And from those observations, set a limit on the deformability of a neutron star and hence the radius of a neutron star. Okay, and I'll show you the LIGO results But before I do that, we want to talk about measuring not the radius of a neutron star, but the radius of a lead-208 nucleus with the PREX experiment. And so PREX actually uses the weak interactions and parity violation. And so Paul's going to talk about that. But let me just say, the weak interactions look at something called the weak charge. And the weak charge of a neutron is actually big. So a neutron has no electric charge, but it has a big weak charge. So the weak interactions are a way to locate where the neutrons are in a nucleus. And what's actually measured is called the parity violating asymmetry, A. And this is the fractional difference. So the cross-section for scattering electrons, the cross-section is basically the probability for an electron to scatter from a lead nucleus when the spin of the nucleus of the electron is pointing in the direction the electron is moving. And there's a very tiny difference, different probability for scattering electrons with spin in the opposite direction. So PREX measures this very tiny difference for scattering electrons depending on the direction of their spin. And this asymmetry allows us to get at what's called the weak form factor. And basically the weak form factor depends on the distribution of weak charge. And the distribution of weak charge is basically the distribution of neutrons. So by measuring the parity violating asymmetry, we can learn where the neutrons are in an atomic nucleus. So let me allow Paul to say some more about how we actually measure this parity violating asymmetry in the PREX experiment. And then at the end, I'll compare that to the LIGO results for the deformability of a neutron star. So let me pause here and let Paul take over.
See if I can find my, here. Okay, here we go. Okay, can everyone see my slide?
Yes.
Okay, thank you. Okay, well, let me start by just talking about how we measure the shape of nuclei in the first place. And the idea is to use elastic scattering of electrons. It's an electromagnetic interaction. So basically you're probing it with a photon. The basic parameter we measure, you have both the energy and the angle, something called Q squared, which is basically 4 EE prime sine squared theta over 2 is the quantity that things depend upon. We have a little q that's about the square root of q. And the idea is that the wavelength at which we probe it is given by lambda equals h over q. So when we look at things at different values of q, we're looking at different scales of size. Now in the middle, we have this a figure showing data of elastic scattering from lead. And one feature is that it covers about 12 orders of magnitude. As you go up in Q squared, the cross section goes way down. And you have all these wiggles. These wiggles are a diffraction pattern due to the shape of the lead nucleus. And if you Fourier analyze it, you get the picture of the right for the lead nucleus, and that's where it comes from. And then it's been done for all kinds of different nuclei. Another example is calcium-48, which is neutron rich. We also recently took some data on that, and I'll talk about that a little bit also. Okay, so that, but as Professor Horowitz said, basically the photon basically only measures the proton distribution and doesn't tell you anything about the neutron distribution. In order to do that, we have to use the weak interaction, and the tool we have is something called parity violation. And I'm going to give a little bit of history of how some of this stuff works now. And basically, parity violation basically has to do with when you look at a physical process, and the question is, if you look at it in the mirror, is it exactly the same? And it used to be thought that all physics interactions, whether you looked at them in the mirror or not, would be exactly the same. And Professor Wu in the 50s discovered that actually that is not true in at least one particular process, namely the radioactive decay of cobalt-60. And the idea is cobalt-60 has a direction associated with it. You can align it with a magnetic field, which is technically very challenging, but they managed to do it. And then the idea is, does the electron come out parallel or anti-parallel to this magnetic field? And if you have parity symmetry, when you reflect it in the mirror, basically the B doesn't change, the momentum of the particle does change. And it would say you should see the same number of electrons going up as electrons going down. That was the parity conservation prediction. It turned out to be totally wrong. The electrons always go anti-parallel to the magnetic field. And that established the existence of parity violation. But this is a special interaction where the nucleus decays to an electron, and a neutrino, it's what's called a charge interaction. It changes the charge of the nucleus. Now in electron scattering, you have a slightly different thing. You're not changing the charge of anything. And the idea is if you scatter electron from a target, then look at it in the mirror, you flop everything except the spin, and it looks like this in the mirror. And then the other symmetry, which we know we have, is spatial symmetry. If you rotate something, if you look at it from the front or back, it's always going to be the same. And when you rotate it, it looks like this. And you compare the picture on the right with the picture on the left, and the only thing different is this arrow, which is the spin of the electron. So basically, if parity is conserved, whether you scatter with right-handed electrons or left-handed electrons, you should get exactly the same thing. If there's a difference, and this parity violating asymmetry here is basically the difference between the left and right cross-section, and that if that's non-zero, it must be parity violation. And it's basically, we take this ratio and we get something. It's actually very small because G Fermi is very small. It makes it very hard to measure. The asymmetry is like 10 to the minus 4 times Q squared, and Q squared can be as small as like 0.01. So we're looking for things that are at the part per million level. Now the challenge that you have is that measuring cross sections to 1% is a big challenge, and we have to measure it many orders of magnitude more precisely. And one trick is when we measure this asymmetry, the ratio of the two cross sections, things like how thick the target is and how intense the beam is, tend to cancel out. And because of all these cancellations, we can do very precise measurements. And again, one thing to keep in mind, the Q squared is important, an important parameter. It discovers the ratio of the weak to electromagnetic scattering, which tells you how big the asymmetry is. It determines the scattering rate, and if it's a small asymmetry, you need lots of events, so you need a high scattering rate. And the final thing, it gives the size of the structure that's proposed. So again, now we want to measure the weak charge distribution. We're scattering with longitudinally polarized electrons, and so you can exchange both the gamma and the Z. The Z is the weak interaction. And again, the point is basically the gamma sees the protons. So the parity conserving piece shows you what the proton distribution is, and the Z sees the neutrons. So the parity violation tells you what the neutron distribution is. Now, the problem is we can only get enough beam time to run at one value of Q squared, but it turns out where this arrow is, there's a particular value of Q squared where the asymmetry is most sensitive to the scale that we're interested, namely the difference between the radius of the proton distribution and the neutron distribution. So basically we measure it at 1 Q squared. All right, now the next trick is how do you get polarized electrons? And this was first done in the 1970s, a group led by Vernon Hughes. They had this very complicated apparatus here. You take lithium, which is very reactive, and heat it up till it boils, and the beam comes out, and you polarize the lithium with a 6-pole magnet, and then you shine UV light on it to ionize it, which is quite a challenge because lithium is very tightly bound. And then you accelerate it and align it with a magnetic field, and voila, you have polarized electrons. And then to prove that it really worked, one thing you can do is you can scatter the polarized electrons from polarized electrons into magnetized iron. And there you get a non-parity violating asymmetry, which tests the method. And it's a lot larger, and that was easy to see. And in fact, in the mid-70s, it was established that you could do that. All right, then the next question is parity violating at all? And at the time, we have this theory of particle physics called the Standard Model. And it was in the 70s that this was established. And in mid-70s, the question was the neutral current, was the Z parity violate parity or it did not? That was a big controversy. There was some data that came out that suggested it was parity conserving. And these experiments were all very difficult. But then Charlie Prescott and others in 78 did an experiment where they scattered polarized electrons from deuterium, and the data is shown in the right panel. And the idea is that there's certain tricks you can play. They used a different source. They used a laser, polarized laser beam scattering off a crystal, producing polarized electrons off the crystal. And then they had this other thing they could insert in the beam and change the sign of it, and nothing else would change. So you take some data with it in one orientation, take it with another, and the sign should flip. And then in the data, you see the open circles are done with one side, with one orientation of the prism, and the black ones with the other. And basically all the black points are below the line, and virtually all the open circles are above. And that's a clean signal for parity violation. And it was very convincing data. And once they showed it, everyone accepted that the neutral weak current violates parity. And then the nice thing there is that this says that we now have a new tool that we can use for a number of things. And one of them is studying the neutron distribution. Okay, so that experiment is shown on this plot, E122. This plot shows on this axis here, the horizontal axis, this is the size of the asymmetry. And so the one that established parity violation was a symmetry of 10 to the minus 4, which at the time was considered incredibly small because sort of 1% was the state of the art without using the asymmetry technique. And well, the idea is today we're proposing experiments that are like 5 orders of magnitude more sensitive than that. So there's been a huge amount of progress. And then the other thing is that when you measure the asymmetry, it's also, you want to measure it as precisely as you can. And things like the beam polarization enter into that. That has to be measured precisely also. So the vertical scale is the size of the error in the asymmetry, and what's relevant is the relevant error. So if it's on this line, it's 100%, which doesn't say very much. 10% do a little better in this direction, you have a pretty clean effect, and you get towards 1%, you can actually measure some things very precisely. So this history, it's been a number of years since then, but there's been a lot of progress, an improvement in high intensity electron sources, high quality beams, so you get the noise down. Precision polarimetry is critical, and also you need high power targets. So basically now we have this tool of measuring small asymmetries with high precision. And again, to summarize, there are two technical challenges. One, how do you detect such tiny effects? And two, how do you measure these tiny effects at the percent level? So the basic technique is that you repeat the experiment over a very short period of time, and then repeat it a huge number of times and average it, and take the average and hope you understand your statistics. And if you know anything about statistics, we usually assume that statistics are Gaussian. When you make a bunch of measurements, they follow this bell curve. Here I've taken our data and I've put it on a log plot, so the bell curve looks simply like a parabola, so it's easy to see what's going on. And this shows our data, and it shows that we can go down like 6 orders of magnitude, and we almost follow exactly this bell curve, which is quite remarkable. But it's this idea that we take very many short measurements. You know, we flipped it 300 million times, and the idea is when you repeat a measurement, you get to divide by the square root of the number of times you do it if nothing else goes wrong. And the idea is the square root of 300 million is a very small number, and that's how we get our precision. So the laboratory we do this is called JLab. It's located in Newport News in Virginia. It's about a half mile. It's a racetrack design. There's an injector here where you inject the polarized electrons, and on the left is a picture of what you have. You start out with a laser, and the laser goes on the gallium arsenide crystal, which makes the electrons that come out here. And the whole trick is controlling the laser. We have something like a half-wave plate to do slow flips, the Pockels cell that does the fast flips to make the basic asymmetry. And all this apparatus is here, and then it can go around a few times and then come out. And we do it in this hall here, hall A. There's also hall B and hall C, and we work in this hall. Now, actually, for P-Rex and C-Rex, we're running at fairly low energies. So we just go around here once. We don't go around this thing and go in directly, because we want to run at a fairly low energy. And then in hall A, we have a fancy spectrometer. I'll say a little bit more about it later. Here is the picture. And basically what you see is pipes supporting the infrastructure. It doesn't tell you much about what's going on. So I'll give you another picture later. Okay, so the idea is that we have to get a lot of statistics to get the errors down. And our target is lead. And when we put a lot of electrons on lead, we tend to heat it up. I don't know whether people do it anymore, but when I was a kid, we used to have lead fishing sinkers, and you'd put the lead fishing sinkers in your frying pan and heat up the frying pan, and the lead would melt. It was really cool, and it was really shiny, and you know, all the dust on the surface would go away, and it was a lot of fun. But that's not considered safe anymore, and no one does it. So the way we do it here is that we have these targets, and then to keep them from melting, instead of putting them on the oven, we keep them at almost liquid helium temperature, and then we put this intense beam on it, and it heats them up like crazy, and it's sort of a delicate edge. And the targets work for a while, and then after a while, here's a picture that's sort of an X-ray of it that shows the density as a function of position, and it becomes non-uniform and makes a total mess, and then it falls apart. But all we did, we made 10 targets. So if we break one, we go to the next one. And so what? Even though it's separated lead 208, we were able to get a lot of it. So that's how our lead target worked. And for calcium, we had to get a calcium target. It has to be isotopically separated. So it's very expensive. And we only had 2 targets. We were only supposed to have 1, but there was unfortunately an accident. And it got overheated and it evaporated. But It was only $750,000. So, you know, what's that among friends? So anyway, we able to replace the target and do the experiment. And, you know, managing calcium is a little bit tricky. Your teeth aren't pure calcium. They're rather, you know, robust to chemical environment. The pure calcium is a problem. So we had to treat it very carefully. Okay, so that's the target, 2 targets for the experiments. And now let's talk about the spectrometer in a little more detail. And I have a little schematic on the bottom here. And you have the target, and then there's a thing called a septum, which enables us to take data at small angles and brings it to a bigger angle where the spectrometer works. And there are 2 quadrupoles that focus the beam like lenses. And then the big thing are these dipoles up here that bend it a lot. There's another focusing thing. And the idea is you focus the elastic peak on this line. And we need to measure the parity violation just for the elastic scattering. If you excite the nucleus, you get a different asymmetry, and the interpretation is completely different. You have to be sure that you'll have only elastic events. And the idea is they lose a little bit more energy, and they bend a little bit more, and they miss the detector. Then the spectra are shown, one for calcium, one for lead, on the 2 figures on the right. And on the calcium, we see here some inelastic levels, and our detector is located beyond that. So none of the inelastic levels are detected. So that's how that works. Now, another problem we have is that in order to measure the Q squared, we have to know exactly what it is. The asymmetry is proportional to Q squared. So we have to understand that at the percent level, and that has to do with the scattering angle. You know, this big complicated apparatus and things, you know, move around with temperature and whatnot, and it's a little bit hard to control. So actually to measure the angle, we come up with this very clever technique, is that you basically use water as a target. And water consists of both hydrogen and oxygen, as everyone knows. And oxygen is heavy and water is light. And the idea is that when you scatter from a nucleus, there's a little bit of recoil, and the final energy is not exactly equal to the initial energy. There's the energy loss due to the recoil. And since hydrogen is lighter than oxygen, the energy loss is larger. And then we can see the 2 bumps, and we can very precisely measure this difference in the energy loss between the two nuclei. And then there's a formula that relates that energy loss to the scattering angle. And basically, this is the data we use to measure the scattering angle precisely. So we get a very precise number. And it's an example of an important thing you have to do to control the systematic errors. Okay, another feature is that the rate is about 2 gigahertz. The pulses come at, less than a nanosecond apart, and that's too fast for the electronics, so we can't count individual pulses. We have to integrate it. And the way we do is we have quartz, which is sort of like glass, and when electrons go through it, they give off something called Cherenkov light, and we detect the Cherenkov light. And the thing is, with this kind of radiation, you take regular glass, it'll turn black. So this is a very special glass that maintains its transparency. And then the issue is, since we integrate, if you count, every event counts as 1, which is what you want. It does the statistics right. When you integrate, you actually have a distribution, and it's like shown in this curve on the red. And the idea is that sometimes an event might come with a very low pulse height, and other times it might be 10 times higher, and that tends to mess up the statistics. And so what's important is to have this peak be as narrow as possible and have as small a tail as possible. The problem is you make it thicker, the tail, you get more light, this gets narrower, that gets thicker, so we have a compromise. The difference between the red and the black is we have 2 detectors, one behind the other for redundancy, and the one behind, the problem is that the electrons produce delta rays that produce additional signal and fatten out the distribution. So anyway, we optimize this, and that's how we deal with the very high rates. Okay, there's another problem in the cross section depends very strongly on both the beam energy and the position of the beam. And although the beam at JLab is incredibly stable, jumps around at say the 10 micron level, but the problem is that at the scale we're talking about, 10 microns is a huge thing, and it can produce all kinds of noise and whatnot. So we do two things to take care of this. One is we have a bunch of beam monitors that measure very precisely for each window the position and energy of the beam. And then we have another thing further upstream, a beam modulation system that we use to calibrate the beam monitors and calibrate their effect on the apparatus. And this is a very important part of the experiment. And these are called beam corrections. And basically the idea is you have a raw asymmetry and you correct it for various coefficients times the differences in the beam monitors. And basically, if we do not make the corrections, we get the black curve. And if we do make the corrections, we go down to the red curve. So the width, and this is for one set of 4 helicity windows, it goes down from 236 ppm to 82, which is about a factor of 3 improvement in our error. And of course, that factor of 3 is very important. It's important that we did that. And there's another thing is that when you change the helicity, you actually change some of these very same parameters that cause noise. There's also a systematic effect. But basically, you measure the systematic effect with the monitors and correct for it to take care of the systematic error. And that uses lots of fancy math like Lagrangian multipliers, which we all learn about our graduate courses that we take in graduate school. So this part of our education is very important. Okay, another important issue is how do you measure the beam polarization? The symmetry you measure is proportional to the beam polarization. We have to divide it out, and that has to be done sufficiently accurately so it doesn't blow up our error. And these measurements are very different, and they can have all kinds of systematic errors. And our method of doing this is that we measure it in 2 completely independent ways. And then we analyze them separately and then compare results. And if they agree, we're happy and we can publish the result. And if they don't agree, we're in big trouble. So the simplest method is the one on the right. We scatter from a magnetized foil. Methods have improved over the years, and we have this down so it's sub%. We polarize the iron in a 4 Tesla magnetic field so we know what's going on. This can be done every few days. It's an intrusive measurement. The other method, which is perhaps more interesting, is what's called Compton polarimetry. The idea is we run the beam through a cavity that has a laser beam in it. And the idea is we're scattering our electrons off light in a cavity. And it's sort of hard to believe that that would do anything, like light doesn't do very much. But the fact is that you do get a number of MeV energy photons that come out and then are detected in the detector here. Getting it to work is very challenging, but we were able to do it. And this thing, since when you have an iron foil, it totally blows up the beam and messes it. When the beam passes through a laser beam, it doesn't do anything. So while we're running the delicate experiment, we can also take this data at the same time, which is one of its nice features. And so we have 2 independent, and they have different pluses and minuses. And then to show you the data here, this was taken during CREX. And it looks like the data is kind of noisy, but if you look at the scale, percent is 2 boxes here, and our errors are small compared to that. And there are 2 important things. Like one thing is this cyan thing here is a Muller measurement, and these other measurements here are Compton measurements. And gee whiz, they agree. That's great. And you also see the beam polarization actually can vary with time. Sometimes it does, sometimes it doesn't. So there's sort of reasonable ideas as to how this works. And So we have all this data, so we believe we can get a reliable measurement for the polarization. The average Compton measurement was 87.1 with a 0.5% error, and the average Muller was 87.06, and unusually good agreement with a 0.7%, about a 1% error, and we combine the two to get this result. That's probably the best this has ever been done, but whatever. Okay, so finally, we move on to our result. And here I show 4 points. And if you remember the picture from the first experiment, we could show the plus and minus helicities on the same graph. Over here, our symmetry is 500 ppm with a very small error. And the other, it would probably a meter on the other side if we plotted it that way and you couldn't fit it. So what we did is we changed the sign of them so that they all should line up. And we basically have 4 different measurements. In and out refers to having the halfway plate, which flips the asymmetry. And then we have another thing called a Wien filter, which does an additional flip of the asymmetry in the accelerator. And so we have all these different measurements. When you average them, a number of systematics can cancel out, but we didn't even need to cancel it out. They all agree. And this gives credibility. So our finally result is 549.4 pluses minus 16.1. That's what the computer said. But this is blinded. And what blinded means is that when they take the data, there's a secret number that's put on that shifts the asymmetry. So the problem is if you don't blind it, you're analyzing your data and you look at the asymmetry and say, hey, this is an interesting result. And if it were a little higher, it would be more interesting. And then you have some data that you're looking at, and do I keep this data or I don't keep it? And then you find, gee, if I keep it, it goes in the direction I want. And if I don't keep it, it goes in the wrong direction. So I bias to keep it. And that can be a very serious kind of bias. There's really no way to avoid it. But if the number is blinded, you don't know which way you want to push it. So you can't bias it. So that's how we did it. And then here's a list of the systematic error contributions. They're all, the issue is we want to keep the systematic error below the statistical error. A number of reasons. One is this statistical error. We know what it is. We had the nice Gaussian. We have plenty of statistics. We know exactly what our statistical error is. Systematic errors are always very hard to estimate. They're probably not Gaussian, but if they're small enough, it really doesn't matter that much. So again, our beam polarization was one thing at about 1%, and beam corrections were 0.5%. You know, other small corrections, carbon dilution, all that. So we work out all these systematics. It comes out to about 0.15%, and our statistical error here is 3%. And for C-Rex, we have a similar table and whatnot, and we have our blinded asymmetry. And then finally, we unblinded it, and it goes from blinded to unblinded. This one didn't change hardly at all. This one changed a lot. Like this one was really nice. It changed so much that our error even went down. That was fun. But anyway, here's our results, and they're symmetries, and they're, you know, reasonably precise, and we're always happy about it. And then what you have to do is take the asymmetries, and which by themselves mean nothing, but when you know the Q squared and have a little bit of theory, you get the result. And the way I'm going to handle that, well, let me first of all acknowledge all the collaborators. A lot of students worked on it, postdocs did all kinds of work, Hall A, Tex. And the other thing is that Professor Horowitz and others have given us a lot of theoretical support and insights, and they know how to convert the asymmetry that we measure, which by itself doesn't mean very much, to some serious physics. So I'm not going to hand things over to Professor Horowitz, and he will tell you what the implications of these numbers are.
Great. So thanks, Paul, and thanks for all the incredible hard work of the collaboration. So just to try and keep things efficient in the remaining 5 or 10 minutes here, the result for lead-208, this parity violating asymmetry, as Paul described, is about half a part per million. That's 550 parts per billion. And then here's the experimental error, which is mostly the statistics. And I said at the beginning that this depended on where the neutrons are. And from that asymmetry, I inferred that the neutron radius in lead-208 is about 0.3 Fermis larger than the proton radius. So the proton radius, the size of lead, some 5.5 Fermis, and then the neutrons stick out by 0.208, 0.28 plus or minus 0.07 Fermis. And so I want to compare that now to the radius of a neutron star. So in this plot here, I've got the radius of a 1.4 solar mass neutron star. This radius is in kilometers, from 12 to about 15 kilometers. Up on this axis, we've got the neutron radius of lead minus the proton radius. So this is the thickness of the neutron skin. And this is in Fermis. A Fermi is 10 to the minus 15 Fermis. So we're going to put the P-Rex result here. And then finally, on this third axis, we have the deformability of a neutron star. So this is how much the gravitational field of one neutron star deforms its companion. And this is the quantity that was measured with gravitational waves. And then finally, we've got a series of blue points. So the blue points are theoretical models. These are relativistic density functional models. These are models of how the energy of neutron-rich matter depends on the density. And given one of these models, we can predict the structure of a neutron star, its radius and deformability. And we can also predict the structure of the lead-208 nucleus and how much the neutrons stick out compared to the protons. Great, so let me start with gravitational wave observations. The gravitational wave observations set an upper limit on the deformability. So it's this yellow region. The deformability is observed to be relatively small, below, so it's 600 or less. So this low region is the region favored by the gravitational wave observations. And if we compare that to our density functional models, and we said the deformability went with the radius of a neutron star to something like the 5th power, and that's this solid blue curve. So if you compare the LIGO measurement to these blue points, we infer that the radius of a neutron star is less than about 13 kilometers. So the gravitational wave observations suggest that neutron stars are 13 kilometers or small. And now let's look at the P-Rex result from the parity violating asymmetry that Paul talked about. We infer the neutron skin in lead, and that suggests some of these density functional models, and those models predict neutron star radii of about 13 kilometers or larger. So P-Rex is suggesting neutron stars are 13 kilometers or larger. LIGO and gravitational waves are suggesting that it's 13 kilometers or smaller. So there's a slight tension between the measurements, but the combined result would be that neutron stars are around 13 kilometers, but you would like to reduce the experimental error, which was a very hard one in PREX, and you'd also like to have a more accurate measurement of the deformability of the neutron star with gravitational waves. And this is where we are now. Great, so let me close with just a couple words of the future. So let me start first with gravitational waves. The Einstein telescope is a proposed next generation gravitational wave detector to be built in Europe. This detector would consist of an equilateral triangle, 10-kilometer arms, the series of laser interferometers to precisely measure the length of these arms. This detector would be 10 times more sensitive than the existing LIGO detectors in the US and the Virgo detector in Italy. The Einstein telescope, along with the similar Cosmic Explorer, which is a next generation observatory proposed for the US, these could very accurately measure the deformability of a neutron star. And so we'll learn, for example, the radius of a neutron star much more accurately than the present LIGO observation. And then finally, at Mainz, a new accelerator, MESA, which is a very high current, low energy electron accelerator, is being built. And the Mainz radius experiment, MREX, will use this MESA accelerator and a large acceptance detector to basically repeat the PREX measurement on lead, but to get better statistics, taking advantage of the high intensity of the electron beam, so that can significantly improve the error bar on the existing PREX. And so I'm a theorist, and I really want to emphasize all the hard work of the experimental collaboration. And thank you again for the chance to talk, and happy to answer questions.
Okay, thank you, Professor Horowitz and Professor Sauder, for your very interesting talk. So let me remind you that our guests can write their question in the chat. Okay, so here we have a question for you. So how does the parity symmetry breaking activity take part in the neutron stars and gravitational wave study?
It's an interesting question. The weak interactions which give rise to parity are weak. So in general, the effect of parity violation is very small. So that's why Paul had to work so hard to measure this 10 to the minus 6 asymmetry. So the short answer is the weak interaction by itself is a small correction to the structure of a neutron star. But neutron stars are made in these supernova explosions where they radiate a tremendous number of neutrinos. And those neutrinos are produced by the weak interactions. So actually, the supernova explosion, the weak interactions are very important in the birth of the neutron star rather than in the structure.
Okay, thanks. So a question maybe concerning to the first part of your talk, Professor Horowitz. Can you please define again deformability?
Sure. So it may help. Sometimes we use the term polarizability. And so what it is if you started with an initial state, which is a spherical neutron star, and you apply the gravitational tidal field of its companion to go to a deformed final state. So this is basically the induced quadrupole moment. So you deform the star to make it non-spherical, and the deformability is a measure of how much a given gravitational field actually induces or changes the shape of the neutron star. So how much of a quadrupole moment or how elongated is the neutron star after you apply the gravitational field?
Okay, so no more questions? No? So thank you once again, Professor Sauter and Professor Horowitz, for your very interesting talk.